There we go. So, did you have a good weekend there, Dan?
Yeah, it's been adventurous with lots of construction around the house
Mm-hmm.
the last 2 weeks. So,
Right.
but it's been okay.
How about the observatory, the all-important observatory?
Yeah, I don't know if I told you, they called me to come pick up the pier top.
Oh,
And
you did.
right.
Yeah.
Yeah, so it's still not back yet.
Mm-hmm.
So I'm going to be out of town tomorrow and Wednesday, and then I'm going to call him sometime Wednesday, and if I haven't heard from him, come on, let's go.
That's right.
At this point, anything, just. But of course, it's been raining so darn much, I couldn't really have concrete poured anyhow.
That's true.
It's just this weather has been horrible.
I know. Well, it's good for all the aquatic animals out there,
I suppose.
And
it's good for the mushrooms. We have fungi popping up all over the land.
We sure do.
And everything is growing so fast, and we have no dry weather to go out and trim and cut and mow.
Mm-hmm.
So
I'll have to get some mushrooms and try to get some of the spores for my microscope program.
Yeah, I have oodles. I have different species, all kinds of stuff.
Cool.
So
anything poisonous or?
Yeah, I don't know.
You don't know till you try. You have to taste each one and find out.
I'm not a mushroom fan of edible mushrooms anyway, so I'm not in much danger.
Oh, I see.
But I don't. Usually, the poisonous ones look interesting. I just get the brown and white ones, and there's some tree fungi that are growing on trees that have gotten blasted by lightning and then fallen over. So we've got some wood fungi.
Yeah. We had some big branch lightning yesterday afternoon.
Oh, really?
Yeah. You can see it looked like over Bella Vista or something.
Yeah, we've just been wet. And we have a little creek on our property that drains, I don't know, about 40 acres north of us.
Mm-hmm.
And when we're doing work with the tractor and that's dry, we just drive across and it's fine. And when it's wet, we drive across it too, but my tractor has chewed up the ground for about 5 meters on either side.
Yeah.
It's just slippery, muddy, and like I said, it's been crazy.
Well, it's cool you have a tractor, like a regular farmer's tractor.
We have a John Deere 1 Series, so it's 26 horsepower, which doesn't sound like much, but it has so much torque.
Geared down. Yeah, that's right.
Tree fall down, and we cut it up into about 20-foot sections, tied it with a chain to the back of this tractor, and we're talking 12, 15-inch wide logs that are tapering as they go up, but we were towing those uphill up the driveway. And like, no problem, just up we go.
Well, we'll have to have a science project where, like, somehow you're able to overcome the pulling action of a tractor, so I don't know.
The tractor is fun because it's little wheels, and where we are on top of the mountain, we have very little soil. We have only 1 inch to 2 inches of soil anywhere, and then it's rock.
Yeah.
And if you get going downhill and it's wet, it's either very wet or very dry, you jam on the brakes and you just start stripping the soil and sliding down the hill.
Oh my God, that'd be scary on a tractor.
Yeah. And of course it has no suspension. It's just the wheels, and they're not that bouncy because they're filled with liquid for ballast to make it heavier.
Oh, I did not know that.
We do have 4-wheel drive, so we haven't gotten anywhere we couldn't get it out of yet.
Uh-huh.
But
tires filled with liquid. I used to work on a farm. I would have never guessed.
Now the guy who was building our deck built his trailer.
Yeah.
And then he found he couldn't get it out because the truck was slipping, sliding sideways down.
So Lucius Capitan is going to know when the stream starts. It's actually starting right now, so you're here just in time. And here we are, everybody. Scott Roberts here with Dr. Daniel Barth.
Hi, everybody.
And we're back again for another great episode of How Do You Know?
That's right.
Yeah, and this time it's about Galileo's 3 great ideas, right?
It is. It's tides in the moon. And we're going to look at, this is the start of a series of 3 episodes, Scott. And we're going to do tides in the moon today. So this is the local effects of tides in the moon. Then, and this is going to be a lot about Galileo. Then next week, we're going to go to French, I believe, 18th century scientist named Edouard Roche. In English, his name would be Eddie Rock, which would be the coolest name ever.
That'd be the coolest name ever.
And Eddie came up with this lovely idea called the Roche limit.
Okay.
And it turns out, you think about, gee, moons can be anywhere. Well, no, they can't. And Eddie was the fellow who proved that's true. And so we're going to do Roche effect and rings next week. And then for the 3rd episode in this sequence, that's 2 weeks from today, we're going to go to Mars, and we're going to take a look at the moons of Mars, because the moons of Mars are really fascinating when it comes to gravity and tidal effects, because one is slowly slipping away and the other is in a death spiral, spinning down and towards the surface of Mars and crashing. So it turns out you can't put moons anywhere you want, and moons are never, the orbits are never stable. They're always either spiraling in or spiraling out, and that all is tied in with tides and tidal effects. So the next 3 weeks, I encourage everybody to join in. Follow this 3-week sequence. It's kind of, we haven't done this before. It's kind of like a multi-part episode in a TV series.
Okay. With like cliffhangers in between, I assume. So
yeah, we're going to, cliffhanger, we'll try cliffhanger. So today we're going to talk about tides and gravity. Galileo struggled with this. Everybody in the 17th century struggled with this, and way back to Aristotle. All your sailors from prehistory, anybody having to deal with ocean, even coastal sailing, understood that there are 2 high tides a day. So every 6 hours you have high tide, low tide, high tide, low tide. And Galileo was one of the first scientists to mathematically investigate gravitation, and he quantified acceleration. He came up with this lovely idea that everything falls at the same speed, which leads us to inertia, which we've talked about in our pendulum episode. And so he had this intuition, really, that the moon was tied in with tides, that the moon was effectively the causal agent for tides on Earth. And we're going to take a look at this kind of from a modern perspective. We understand the idea that gravitation is one of the 4 fundamental forces in the universe. Gravitation is universally attractive. Everything pulls on everything else. And we also understand, courtesy of Newton, the 3rd law of motion, that for every action, there's an equal and opposite reaction. And of course, when we're talking about any 2 bodies in space, like the Earth and Moon, any planet and its moon, any sun and its planets, that the gravitational action is reciprocal. Now, one of the things we're going to take a look at, Scott, one of the things that I always have on hand for my astronomy STEM labs, one of my favorites is, and of course I dropped it.
Is it a softball
I am not going to make second base on anybody's team. This is a regulation Tball.
Tball.
And this is a Rawlings official Tball, and it's leather covered, but it's a rubber ball. The nice thing about a rubber baseball is that we can cut into it, and we're going to do lots of fun things in upcoming episodes. But if you stop by your local sporting goods store, and if you want to participate and follow along with these, go ahead and pick up a few rubber T-balls. Yes, in high school, I made the freshman team and I was a pitcher. but I wasn't good enough or strong enough after that to stay in baseball. But we have these Tballs. And the other thing we need everybody to understand is that when you model the moon and the Earth, it's really difficult to do on a tabletop. This is a reasonable model of the Earth and moon. We have here, this is just a rubber playground ball like everybody has seen, and here's a baseball. And if you measure it closely, the baseball is about 1/4 the size of this rubber ball.
Okay.
And that's the scale of the Earth and moon. The moon is about 1/4 the size of the Earth. And you can model this in lots of ways, but a basketball, soccer ball, and then a baseball gives you a pretty good idea. But the fact that I'm holding them up here together, I'm cheating, because although it's in scale in terms of diameter, it's not in scale in terms of distance. The moon is 30 Earth diameters away. This is the trigonometric measure that lots of people, I think Eratosthenes first came up with this in about 500 BC, that the moon is about 60 radii or 30 diameters. So this is a 1-foot ball, a 30-centimeter ball, for our friends in Europe. And so for this moon to be in proportion, if this is a scale model, this moon has to be 30 feet away, or if we're at 30 centimeters, that's 9 meters, I think that works out to be. So is that right? I'm not sure. But it comes out to be, it's quite a ways. It's about 10 meters away. So obviously we can't hold this model in our hands. I frequently do activities for people where I say, okay, here's the Earth and the moon. Now let's show you how big it is. We put the big ball in the center. We get some string and some chalk, and we go out on the playground tarmac, and we draw a big circle, and it's 60 feet. That's about, let's see, 30 feet is about 10 meters. So it's about 20 meters in diameter. It's a huge circle. And you look at this moon and you go, oh my gosh, the moon is lost in this gigantic circle. And you go, okay, you want to see an asteroid with a near Earth pass? You take a grain of salt and you drop it somewhere in the circle. Ooh, there's an asteroid inside the orbit.
That might be a big asteroid.
That's right. That would be a fairly large asteroid. That would be something that would destroy a city. And so we have to make some allowances today. Space is really, really big. Planets aren't that big at all, and moons are really quite insignificant in terms of the sizes of orbits. But today, we're just going to deal with the moon. We'll put our Earth ball back over there. And so what we're going to look at today, and I'm going to switch cameras on us, and we're going to take this one piece at a time. So here we go, and I've got this drawn with each of these, of course, is our Earth. That pen isn't working very well, so we'll try a different one. This is our moon up here. And so we've got Earth and moon, and we realize that we have reciprocal gravitational forces. The Earth pulls on the moon pulls on the Earth. Sorry, those aren't quite lined up, but we'll have to deal with that. Now, if we talk about the tides, the gravitational pull of the moon, water is more flexible than stone. Surprise. And so what we see, and I'm going to draw something that's very exaggerated here, and I'm going to try to make sure that I get this fairly accurate here. And we're going to draw what we call a tidal bulge. Now, I will go ahead and color this in so everybody can see it pretty well. This represents a bulge of water that's being drawn up. Now, this is horrendously out of scale. This tidal bulge is nowhere. Am I drawing this correctly? No, I'm not. I'm drawing it backwards. This is nowhere more than about 3 meters. There are places where, there are places in bays and other things where the tidal oscillations build up bigger. But generally on the oceans, you have about a 3-meter tidal bulge of water. Now, that's a lot of water, 3 meters deep, and we're talking spreading out over tens of thousands of square kilometers of ocean. That's a very large mass. That's a very large mass. And this would be the case here for our, I want to make sure I'm doing this right. Is this correct? Oh, it is. This is our non-rotating. This is our non-rotating case. So if the Earth didn't spin on its axis, and we realize that what we're looking at here, this would be the Earth's North Pole. We're looking straight down on the North Pole, and the moon would be orbiting anti-clockwise from this, this perspective. But basically, this would be the case if we had a non-rotating moon. Now, you might say, well, when would we have something like that? Pluto and Charon do this, Scott, because Pluto and Charon are both tidally locked to each other. So Pluto and Charon, the same face.
So the center of the orbit is somewhere in space, right?
It is.
Between them.
The center of the orbit is called the barycenter.
Okay.
And if we draw a line directly through, the barycenter of the Earth-Moon orbit is somewhere deep inside the Earth. Again, I'm distorting it here. It's not that close to the crust. So the barycenter is here, and effectively, these two masses spin around this common point. Mm-hmm. And you can think of this if you have two unequal barbells, right? A barbell with an unequal weight on each end. Well, there is a balance point. And that balance point, and we can do the physics of that. We needn't go into it right now. But basically, yeah, it's a balance of torques. And this barycenter is the center around which the Earth and Moon spin. So Pluto and Charon are both locked to each other. Pluto is essentially, or Charon is essentially a geocentric satellite of Pluto. It hovers over the same place all the time. If you stood in one place on Pluto, you would see the moon Charon gigantic in the sky overhead. It would never move in the sky. It would always maintain its position relative to your horizon. If you were on the opposite side of Pluto, you would never see the moon. It would be quite a surprise to be an explorer who grew up here and traveling around, and by the time you get here, oh my gosh, what's that big thing in the sky? Mm-hmm. So you do have non-rotating situations. Pluto has a crust that's a lot of ices, methane, ammonia, water. They're all flexible. We know glaciers flow. And so although no one's really orbited Pluto to measure this, there has to be a tidal bulge of ice on Pluto's crust. But this is the non-rotating case. But of course, we know that with our own Earth, and let's go ahead and draw the Earth's center right there. Let's go ahead and put the barycenter here. But we know that if this is the North Pole, we know that looking down on it from this way, the Earth spins, and also we'll switch our little moon over to here. We realize that the moon spins also. So they both go around in this anti-clockwise direction, but the Earth spins approximately 30 times faster. Because the Earth rotates once every 24 hours, the moon, on the other hand, takes approximately 29 and some fraction of days. And so we realize that the Earth is spinning 30 times faster than the moon orbits about us. Because of this, in a rotating case, the tidal bulge, because of friction, and again, I'm exaggerating it here for clarity. It's kind of like those boxes of chips or cereal where it says enlarge to show texture. You know the Doritos chips are not that big as the picture on the box. And so what we have here is what we call a tidal axis. And we have the gravitational axis. And we realize that the spinning of the Earth carries the tide ahead by some number of minutes. And so when we look at this, we realize, well, golly, we've got this idea that, and this puzzled Galileo, because Galileo said, if it's the action of the moon, if it's gravitation, why isn't it directly lined up? Why doesn't it line up directly? Well, it has to do with the fact that the Earth is spinning quite rapidly compared to the moon's relatively slow rotation. And this friction across the bottom of the ocean carries and pushes the tide ahead.
Okay.
And so we have this really interesting theory, but we're still only accounting for one tide per day. If this was the case, if it was just gravitation, because you'd think on, oh, the opposite side, well, wouldn't it be sucking the water closer? Wouldn't it be making
draining it into the bottom of the ocean somehow?
Yes, indeed. And I remember talking to my physics instructor who said, oh, yes, gravity causes tides. I'm like, but. He's like, okay, Barth, what is it? I said, well, why isn't there an anti-tide on the opposite side?
Yeah. Is it that you're getting to that there's a tidal bulge due to inertia?
Very, very good, my friend. Very good indeed. Very good indeed. And so we look at the third case, and this second case is the rotating case. But here we realize that, and if we take a look at this, we realize that there's not just one tidal bulge, but there's two. The moon's gravity doesn't just pull the water of the oceans toward it, it also pulls the Earth entire toward it. I used to tell my students the reality of gravity is that when you trip and fall, the Earth rises up to meet you and give you a smack, just ever so slightly. It's not even measurable. But every time when we have this sort of a dynamic, we have to realize that not only is the water being pulled up, but in fact, to some very minor degree, the Earth itself is being pulled upward as well. And so we have this situation where, well, the Earth is being pulled too. The other interesting fact, if we look at the force of gravity when we're talking about, oh, this is 12,000 kilometers farther away, that means the moon's gravitational force on this side is substantially larger than it is on this side because gravity decreases with distance. So the gravitational effect pulling the water is weak on the Earth's far side. But when the Earth moves away, we do indeed get this inertia effect. And I have some, oh golly, let's see. Let's make that big again. I have some images to share with you here. And let's share the first one. So this is an interesting image. So here I am just standing out in my driveway, and I've got a cup. And you might say, well, gee, what are you doing? And I did this demonstration for some students. And what I'm doing here is I'm going to go ahead and yank the cup downward. Now, I planned to go out with a shovel and get a scoop of gravel from the driveway and do this with a cake pan. But it turns out everything is sopping wet today out here at the ranch. So I'm just going to show photos. And what I've done there is I've yanked the cup downward, and the water, because of inertia, remains behind. Now, there's surface tension and all sorts of other things going on there. But when we look at this idea and we think about the Earth being pulled away, what we realize is that, okay, we do indeed have a tidal axis, which runs through the Earth this way. The gravitational axis runs this way. And we end up with two tidal bulges. We end up with the first one here. And this tidal bulge is primarily due to gravity. And we end up with an opposite tidal bulge over here that's not quite as large. And this tidal bulge is caused by inertia. So we have two tidal bulges. This one, there's a force of gravity pulling this way. Here, it's inertia. The Earth is being moved and the water is being left behind. And the Earth's rapid rotation is pulling both of these off of the axis with the moon. But if we go ahead and we look at a line here, we realize as the Earth is spinning, each of these tides, high and low, come around 6 hours apart. And so here we have high tides, and 6 hours later we have a low tide, then high tide, and again a low tide. So we have high and low, 6 hours apart, and it's never quite in line with the moon. It's never quite in line with the moon. I had looked up how many minutes the tide lags behind the lunar position. It's not as much as you might think. I think it's something like 20 minutes. But it's never, Galileo realized that it wasn't quite lined up. And if you figure the Earth is 12,000, it's 40,000 kilometers around, and it does that in 24 hours, it goes about 1,000 miles an hour, or about 1,600 kilometers an hour. So 20 minutes makes still many hundreds of kilometers out from the position lined up with the moon. And so we get this. Now, when we talk about discussing this and understanding it, if you have a great idea of how gravity works, and if you're pretty familiar with how the idea of inertia and how that works, then this kind of makes sense to you. Most people look at it and you take some time to think about it and they go, oh yeah, that makes sense now. Because the Earth is spinning really rapidly, I get that it pushes the tide out of alignment with the moon. And I get that the Earth is moved and the water is left behind, and that creates two tidal bulges. But when you try to explain this at an outreach event or to students, it's a little bit more difficult. So what we're going to do is we're going to go ahead and we're going to use our Tball, and we're going to use a lead fishing weight. This is a lead fishing weight. And this is actually elastic strap off of a COVID mask, something that I'm sure everybody has around now.
Yeah, there's extras around.
There's extras. So we're going to switch this over to the desk cam, and I'm going to show you how to make a permanent model out of a Tball and a couple of weights and some elastic. You could use rubber band material, but I find the cloth elastic from a mask lasts longer. Rubber deteriorates rather quickly. But let's go ahead and switch our camera again, and we'll do some hands-on. So here's our Tball. The tools that we're going to need are a hobby knife and a plain old flathead screwdriver. Now, what I'm going to do here is I'm going to make an incision. So I'm going to say, yes, we'll give the obligatory safety warning, friends. Please be very careful. Don't let students or children do this on their own. This is a teacher, adult, parent style model, and for heaven's sakes, take care. But I'm going to put this straight down so that there's little chance of it slipping off. And I'm just going to plunge the knife in. I kind of feel like an Alfred Hitchcock moment. Oh, and of course there, the knife slips out of the holder. Yay. It really is a live broadcast, folks. Nothing ever goes quite.
That's right.
Supposed to. So I'm widening this slit a little bit, and then I'm going to make 2 more cuts so that it's essentially, I'm cutting an X in the ball. So what I'm doing, friends, is here's my ball, and I'm slicing an X into it. So what I'm going to do now, I have my my weight here, and I can now go, and with a screwdriver, I've got a knot on the end of this, and I can position this, and I can take my screwdriver, and if I do this carefully, I can shove the knot down in there. And with the knot down in there, I'm now going to take some super glue, and I'm just going to give it kind of injection of super glue. And I suppose we should give an obligatory warning about super glue as well.
Yes.
Don't glue yourself to the Tball.
Right.
And I'm going to blot the super glue with a napkin. That's disposable. You also want to always wipe off your super glue tube. And we'll give this a moment. It's already getting solid, but we'll give this a moment. When I was working as a high school teacher with super glue, I would have my students build balsa models of cars and various things. And I would say, okay, there's a couple of rules. First of all, you put some super glue on a piece of tin foil and you use a toothpick and you dab the super glue where you want it. That way you don't get too much. And the second thing is you always wipe off the tube before you cap it. But of course, I'm working with 15-year-olds, so this doesn't always happen. And I said, okay, well, if the tube is clogged, call me, I'll get it unclogged for you. And so I had a student who basically took it and he's squeezing it like it's a bottle of ketchup at Denny's. And of course, the super glue went blurt, blurt all over his hands. His friends are laughing at him. Oh, you should have called the teacher. And he takes his hand and he just flicks his hand like he would flick water on somebody. And it's like he's going to flick super glue on his friends sitting across the table from him. And of course, it didn't land on him. It landed in the hair of a child sitting about 3 desk rows away. And she's like, ah. So yes, please respect your materials, friends.
Yes.
You're dealing with sharp things and sticky things. Let's not try to make it a story that you laugh about because it's only funny 5 years later.
Right. It's funny how those things work. It's funny how things become funny over a period.
It is. And my story is
at
now.
the time, they're not funny at all.
No, I actually had the droplet of super glue actually flew up and it landed on and it glued together the eyelashes of this girl.
Oh my God.
Who's calling me and saying, I can't see. And I said, oh my God. So I took a little pair of nail scissors and a little index card. And I said, okay, I'm going to put the index card here. Hold your friend's hands. Close your eyes. Don't wiggle. And I trimmed the eyelashes off and she blinked and said, oh, it's okay now.
God, how lucky.
I know.
I heard that super glue was actually invented for closing wounds on the battlefield.
It's surgical glue.
Yeah.
And of course, I read the Students the Riot Act about proper use of glue and don't stick yourself and don't put it in inappropriate places and dire punishments, but could you predict this? You can never write enough rules to to have everybody figure out. You can't make anything foolproof, as my old dad used to say, because fools are so darn clever. So what do we have here? This looks like some horrible medieval weapon now.
Yes.
We've got a baseball now with two pieces, and I think we can show this. I'm going to back up a little bit. Here's the original length of the string, and when we let gravitation take over, we'll realize, oh, this is the moon side, and we're seeing, oh, direct gravitational action. This string is stretching a lot. This one isn't. So this is our side closest to the moon where we have gravitational action. And we do actually have a larger tide on that side. And then we look at the opposite side and we say, well, what's going on here? Well, this is inertia. And if we watch and if I pull this up quickly, and I don't have slow-mo, but if I pull this up quickly, and I'll see if I can do it close in the camera here, and I'll get my noggin out of the way so I'm not distracting. And if I pull it up quickly, we see that what happens is the weight lags behind and the cord stretches, right? So if we pull it rapidly, and if we're here, we can bounce this around and everything else. But basically, when we move this one quickly, we have inertia. We all know what this is. Haven't you put groceries in the back of your truck or SUV and pulled out, and oh my gosh, you have to pull out quickly to make the turn out onto the road from the grocery store, and you hear everything go and slide in the back of the car. We've all experienced this. We've all been on the spinning, twirling rides at the carnival or at the county fair, the teacups and the tilt-a-whirl and the octopus. I'm dating myself. But essentially, you would get on these rapidly spinning rides. Did you ever ride, Scott, I don't know what they call it. You go in and you stand against a wall and they spin it really fast.
When they spin and they drop the floor.
They drop the floor.
Yeah. They're probably illegal now.
What we're seeing here is centripetal force and inertia. Really.
I saw some people sliding down, the wall.
Right. So. Your inertia wants you to fly away from the center. The wall prevents you.
Right.
And so you're stuck. You have friction. So we see this kind of thing all the time. We just don't normally think of it in terms of, oh, here's the moon, here's the earth. Oh, look, I have a greater stretch on this side than this side.
Yeah.
This one's gravitation, this one's inertia. And yes, for my friends who are saying, oh, but wait, the tension has to do with the various weights. Yes, I know. But we're making a model to give people an idea how gravity works, because it's really critical to give people an idea how gravity works. So we've got this, and we've got a very nice handout for everyone that will give you an idea and how to model the effects. I did in the handout, I did suggest using duct tape. If you don't want to destroy a Tball, you can use duct tape to attach your strings and weights, and that works just fine. And
I just reposted the link to get that study guide.
Okay. Did you put that up?
I did.
Okay, great. Yeah, people can download the study guide, and these are all fully illustrated. And once again, we've had a short little program to help people understand tides and gravity, and it's really amazing how much you can do with such simple materials. I often look, and my students would often look, and we would say, well, how come we don't have lab equipment? Well, because we don't have money. Well, I don't have money. It stinks living in a poor town. Like, well, yeah, finances fluctuate, kids. You'll realize this as you get older. But of course, yes, finances do fluctuate, and all the activities that I do in the Astronomy for Educators text and on these programs, I try to make these costs about $1 a student or less. So this one costs a little bit more. The two lead weights cost about $1. The Tball costs about $3. So this is a $4 model right here. But do you have to have one for every student? No.
No.
Have one for every group of four, you're still in under the dollar a kid or less rule. And the nice thing about something like this is that if you're talking about students who are working remotely, that's easily done just as we're doing it now. If we're talking about homeschool parents and children, yes, this is something you can do on the kitchen table. If you're talking about astronomy outreach, no matter what, how small your club is, somebody can pony up for a Tball and some fishing weights. You may have one in the garage. Anyway,
You know, Daniel, the cost of, even if you were in a school that had gobs of money, bursting at the seams, and you could buy some really elaborate model, I think it makes it more accessible that it's inexpensive, that this is something that any student can make or any parent can make, so, I think that makes it attractive. And I think it helps to simplify some fairly, complex topics. So, right?
Yes, I found this out early in my first teaching job, early in my career, was at a place called Diamond Bar High School, and it was a very affluent communities, doctors, lawyers, entertainment, sports figures. It was. I could never afford to live there. I commuted and taught there. And when they hired me to start their physics program, they said, here's $40,000 for equipment. Let us know if you want more. This was 40 grand in 1985. It was a huge amount of money, more than 100,000 today, I would think.
Right.
So it was just a ton of cash. And as I was teaching, I found out, we have all these great toys and we have 6 or 7 of each, so everyone can play. And then I found out that, okay, follow the instructions wasn't nearly as fun as can we build it, can we make it?
Right.
And my students said, we tried something. We did a little experiment. We had a heavy duty polycarbonate bottle, and we put a couple of bolts through it. We put some methanol in it. We put a cork in it. We touched a battery coil to the to one of the bolts, and it set off the methanol, and it popped the cork across the classroom. And some of the kids said, well, it's bouncing off the wall. How far does it go? These are my physics students. And I said, well, let's go see. So we took it outside, boom. And, it went 10 meters to 30 feet or so. Okay. Mm-hmm. Well, that's great. And I said, do you think you could make it go farther? And they said, how would we do that? And I said, well, I'm going to give everybody a cork. Go home, toilet paper tubes, whatever, make me a rocket shape, and we're going to plug it into the bottle, and a 6-pack of Coke for second prize, and a couple of movie passes for first prize, and a couple of candy bars for third prize, and we'll just go blast them off. And the kids did this, and it cost nothing. I sacrificed a $3 plastic bottle and
right.
And a bunch of corks that were pennies a piece, and they were all like, oh, wow, this is great. What are we going to build next? They didn't want to work with the expensive insert tab A into slot B type equipment with a list of instructions. Write your answer in the little box, collect the data. Is it this number? If not, it's wrong. And I found out I started doing these experiments where students were making things, and my program went from about 20 kids the next year. They said, well, what the heck is going on? You had 20 people in one class this year. We have 150 signed up. We filled 3 classes and we had to cut it off. And they said, what are you doing? And the answer was making stuff.
Yeah, and you're enabling those students. It's awesome.
Yes.
It's awesome.
And so if you want to know more about that, it's something called the Experience First methodology. I'm presenting at the Arkansas TSOL conference this year, and we're doing it by video. And I will send you a link to the video if anyone here is interested in more scholarly how these sorts of make it, build it, test it activities enhance vocabulary uptake for both English and non-English speaking students. If you want to get more scholarly, friends, I'll send Scott a link and he can hook that up.
Yeah, if you have it now, go ahead and send it to me in chat, and I'll I'll share
I love
it.
that.
But I wanted to read something to you. This is
Certainly.
Lubo in China, and he
Oh,
says,
wonderful.
"What a stroke of luck! I'm going to be explaining tides this weekend on an island trip, and this can really help me a lot." So that's really cool.
That's awesome. I am so
Yeah.
happy to hear that. And what's the person's name?
His handle is Lubo in China.
Bo. If you would like, you're welcome to email me. Any of our listeners, watch viewers are at astronomyforeducators@gmail.com. So I'd be happy to go ahead and send that. And I'm putting this link for the Experience First methodology in chat right now. And I had an awful time with getting this. They wanted a 30-minute presentation, and I did it here at home. And the first time I did it in high fidelity, 1080p, it was too big a file to uplink. So I said, well, I have an Astronomy for Educators YouTube channel where I do things just primarily for teachers. And I said, well, I'll uplink it to there. And it took hours to uplink it, but I got it, and it's there. And so the link is in chat, and Scott can post that and be happy to have you take a look. Okay. And friends, the Astronomy for Educators book, it's a free book. So if anyone would like to see more about these activities, Astronomy for Educators, put it in your search engine, and Astronomy for Educators, Daniel Barth, it'll come right up. You can download that for free. And you're welcome to write to me, astronomyforeducators@gmail.com. I answer every email I get. And Scott has links for curriculum materials, but I have oodles more than the few things that we do here. I have literally hundreds of activities. And so people write to me and say, do you have something for this kind of an activity? If it's astronomy, probably I have something. If it's physics, maybe. A lot of times people have questions. Well, I've seen this activity and I've done it, but I don't know exactly why it works, how it works. So you're welcome to play Stump the Professor. And
right.
I will do my very best. And if I don't know, I'll make up a convincing lie. I'm just kidding. Okay. I will not do that. If I don't know, I'll say so. And that's fun. That's great when I get those questions, because then I get to do some research and dig in and learn something new.
That's right. That's right. That's great. Well, tomorrow we have our next Open Go-To Community Live program. It'll be episode 154. It also happens to be my birthday tomorrow, so if you feel so inclined to want to celebrate that, if you're a Facebook member, I did post something. They have a deal where you can urge people to donate towards a specific worthy cause. And so my worthy cause of the year is Mount Wilson Observatory. It is a nonprofit organization. So my goal is to raise $1,000 for them. So if you feel so inclined to celebrate that, that's great. If you've never been to Mount Wilson, it is really a place to go. We have a once a year trip to Mount Wilson where we have people physically look through the 60-inch telescope. This is the scope that Harlow Shapley used to discover that the sun was not in the middle of the Milky Way, and that, many other discoveries were made with this telescope, but it is the model of all modern telescopes made today, so a lot of
the largest instruments that's still in use for visual work, is it not?
It is. There's a few others. I think that maybe McDonald Observatory might hold the title, with an 82-inch telescope. There is the 100-inch at Mount Wilson as well that they use for visual, okay? But the cone of light that comes out of the 60-inch, where you're just sticking an eyepiece on there, there's no relay lenses or anything. You're actually just looking at the mirror, okay? It's a fantastic sight. Saturn, Mars. I've used this telescope many times. It is absolutely stunning and incredible. And one of the, it is a true diffraction limited telescope as well. A lot of big telescopes are not diffraction limited. So you will see, some just amazing views. I've seen globular star clusters around the Andromeda galaxy and stuff. So they do a lot of public outreach there. And they have these programs. We pay for a night, okay, on that telescope, and we take 25 people for really kind of a, life bucket type of experience. On that trip when we go, and we'll announce it when it's all finalized, but this particular trip will also include a Friday afternoon at the Jet Propulsion Laboratory, where you're going to get to go in and see what's going on there with planetary missions and stuff. And then that evening we would go to, or that Saturday we would go to, no, that's actually the Friday night. We would go to the 60-inch, and then Saturday we're going to be doing some other activities, and then Sunday we're supposed to use the Snow Solar Telescope at Mount Wilson in that morning, and then we let you guys go back to wherever you might come from. But you'll fly in and out of Los Angeles Airport, LAX, and it's an amazing trip. And so I'll be updating things soon.
Yeah. Do you have a date for that?
It would be sometime in September or October next year. Okay. And we've done a couple of them so far, and it's just an amazing experience overall. You'll stand where Edwin Hubble stood. You'll stand where Einstein stood. It is just, you feel the history around you when you're there. So, and you've been up there, I think. Is that right, Daniel?
If I can get my boss to sponsor me.
Yeah. That's right. It makes a nice gift for any astronomy enthusiast that you might think of. So,
yeah, you have to hang a conference name on this, Scott, so I can say, "Oh, boss, I'm going to the."
I'll work with you. You can. We have
conference.
Lectures also during this series. So we'll have. We typically have a JPL scientist or two come up there with us, and so it'll be a great weekend of science and science history, and pressing the eyeball to a massive instrument. So it's going to be a lot of fun. Also, we this Wednesday we have the next Global Star Party, which is number 49. So we're getting really close to the 50th Global Star Party, which is going to be great as well. But for every Global Star Party is special, and we always have special speakers there. And I think that's all I have to share for right now. There's always something new, and we'll be back with you tomorrow at 4 p.m. Central. And you guys keep looking up. And thanks a lot.
We'll see you next week. Bye-bye.
And don't forget to write to Dr. Barth if you have any questions.
That's right. Questions to astronomyforeducators.com. And go ahead and look up the book and download your copy if you haven't already. So there you go, friends. Thank you, and we'll see you next week.
Take care. Hello, everybody. This is Scott Roberts from Explore Scientific. And today I want to talk about the world-famous Galileo Telescope Kit. This is a kit that you assemble by yourself. You'll learn how optics work by assembling the objective lens and also the eyepiece. And there's two different eyepieces that are in this. It's a 25 power, 20 millimeter eyepiece, but it also comes with this very clever little device here that works both as a Barlow lens that will double the magnification of this eyepiece, making it 50 power, or it can be used also as a Galilean eyepiece, which gives 17 power to the telescope. This is what Galileo virtually saw through his own telescope. So you can have that same experience that Galileo had looking at the moon, looking at Saturn's rings, looking at Jupiter. It is a telescope that was designed for the International Year of Astronomy in 2009, and it's a fantastic kit both for child and adult, to learn how a telescope works. And so if you get the telescope like this, you can either have it on a stand like this, you can hand hold it like a pirate's glass, or on the bottom here, we have a threaded hole here that you could put it on a camera tripod. Very versatile, very rugged, and a lot of fun, all from Explore Scientific.